And today's seminar is going to be somehow related to the lectures that Antonio Politi are giving on chaos and nonlinear dynamics, and is basically going to focus on collective synchronization, and is going to be given by Diego Pazó, who is a researcher at IFISC, Instituto de Física de Cantabria in Santander, has a contact with Diego.
Thank you. Thank you for letting me talk in this interesting school. And I'm going to talk about collective synchronization. And okay, first I will start with the concept of synchronization. It dates back to Huygens, who around this date wrote a letter where he found that a pendulum clock like this one, if it was hung together with another clock after some time, they were synchronized in the sense that they oscillated with the same frequency in the phase lock. And of course, the pendulum clocks were non-identical, of course, but due to some interaction, the very weak interaction, they were able to synchronize. And in fact, he noticed that if he perturbed one of the oscillators, after some time, it came back to the synchronized state with the other pendulum clock. And if he hung each oscillator in a different wall, they didn't synchronize. But when they are hung from a common support, they become synchronized. So this means that if the natural frequencies of each oscillators are quite close, some weak interaction allows them to synchronize. Okay, like this case. Okay, there are several examples of synchronization. One of them, for instance, is the Circadian Cycle. That is some internal cycle that we have, some kind of metabolic cycle that our bodies have, such that, if you are prevented from the day-night cycle, but instead you are under a steady illumination, that you will exhibit a certain cycle that is different for each person, but is around 25, 27 hours. But due to the influence of the day-night cycle, you become synchronized with your environment with this 24 cycle time. There are many other examples. I think it became interesting for applications around the 20s of the previous centuries with electric and radio engineering. And also there are continuous developments and continuous findings, like, for instance, the respiratory and cardiac rhythms in a human exhibit some transient synchronized states. This was found in 1998. So, okay, this is synchronization is a very well-known example of nonlinear effect, and I will devote this talk not to synchronization but to collective synchronization. And maybe the most prominent example or most famous example is the example of fireflies. So if you have, it was an observation, a very ancient observation, that in some countries, when you have a swarm of fireflies, they exhibit synchronization. They have even a movie, like this one, where the male fireflies exhibit this blinking, trying to, for the sake of attracting females, but as there is a swarm of fireflies, even if its firefly has, okay, can I put it again? Even if its firefly has its own intrinsic oscillation rhythm, the influence of all the other fireflies make it to synchronize. So at the end, you can see this nice picture where all fireflies synchronize approximately at the same time. Okay, so this is an example of collective synchronization or macroscopic synchronization, because it involves a very large number of oscillators. Of course, the examples do not restrict to fireflies. You have may have also crickets that synchronize the sounds. Also, it was found some circadian clock cells. The sinoatrial node of the hair, for instance, this is an important example because our life depends on this synchronization. Basically, in the hair, there is a congregation of cells that are oscillatory, and they form your natural pacemaker. And when they are synchronized, they give a signal to the heart that it has to contract, and your life depends on this synchronization. And nature could have selected instead that your life depends on one cell, but it's much more robust if your life depends on a aggregation of cells that oscillate rhythmically. And if this doesn't work well, then you better get an artificial pacemaker. But instead, we have usually this natural pacemaker that is made of many cells that synchronize, and there are many examples, examples reported about neurons. Maybe the Parkinson's disease is the most classical example. Also, some ecosystems may synchronize. The clapping audiences. When some audience is clapping, it's usual that due to the influence of the other part of the audience, there is a tendency to synchronize the clapping. Even if they say, we try to avoid it consciously, but actually there's a tendency to synchronize clapping. Also, you can construct chemical oscillators to synchronize. Also, it's famous the case of the Millennium Bridge. If you want to stop here, at least you can read this book. I can recommend it. It's a book about synchronization written by Strogatz that is written without formulae and is, I think, quite interested and it has a vivid writing of this phenomenon. This is the case, for instance, of the Millennium Bridge. It's also quite remarkable, as I said. This was this paper appeared in Nature analyzing it. And basically, this Millennium Bridge was inaugurated in London in the year 2000. And what happened here is that there's a crowd of people who went there for the inauguration of the bridge. And of course, every person is walking, but due to some macroscopic synchronization, the walking of people synchronized, and then the bridge started to oscillate. And this was a dangerous oscillation, and the bridge has to be closed, and some parts of the bridge had to be fixed to avoid this kind of oscillation. So notice that it is not that the bridge is oscillation makes the people to walk rhythmically, because if the people were not there, the bridge wouldn't be oscillating. But actually, even if each person has its own walking rhythm, due to the small interaction provided by the bridge, at some point they synchronize. So at the end, it creates a positive feedback and makes this effect not to be desirable in the case of the bridge. So here I start a little bit with the analysis. As Antonio Panetti said this morning, we have to distinguish between conservative and dissipative systems. As a prominent example of conservative system, you have the pendulum, and as a dissipative system, you have this pendulum clock. But actually, there are many examples, like all these biological oscillators or electrical circuits. So all these also have dissipation. And of course, they distinguish a lot in the kind of attractor. In the case of conservative systems, you don't have any attractor, and your phase space is this one that those of you who are physicists at least will know it. If you are in a dissipative system, instead you have a limit cycle, or you can have a limit cycle, but instead, in any case, any attractor. And the simplest way of providing oscillation in terms of attractors is the limit cycle. So, the limit cycle is actually what you wish if you want to have a definite period or rhythm in your system. Because if you want to construct a clock, you better design something like this with a limit cycle than a conservative pendulum. Because if you have a conservative pendulum, any small perturbation will change it will change your trajectory, and it will change the period. Instead, you want something that is robust enough to have a certain period. So here, if you make a perturbation, you come back to the limit cycle. Okay. So these are dissipative systems. And this is the kind of thing we'll have in mind for the rest of the talk. So, okay, you have an oscillator, like a pendulum clock. You have position, velocity. Then you have a phase portrait where position and velocity are the Cartesian axis, and you have some limit cycle with a certain angle. So, okay, if you take this angle, call it now phase, okay? Synchronization in a strict sense means that your phases are bounded. So the phase difference is bounded. Actually, okay, if you are in the Huygens space, m equal to n, so the frequencies are close, so they synchronize. This means that the phase difference, theta 1 minus theta 2, is prevented of exceeding a certain constant. Okay, so this means that the phases are fluctuations can exist, but the phases have to be bounded. And in particular, this implies that the frequencies should, okay, if n is equal to m equal to 1, the frequencies should be the same. You can also have other synchronization ratio. It's different from 1 and 1. You can have also something like 2 to 1. If one oscillator oscillates at frequency is approximately the double of the other one, then you will have the same relation here, but written 2 and 1. And of course, the frequencies will entrain at a certain rational number that can be 2 or 1/2, and so on. Notice that I'm writing this in the implication there to the right, but not to the left, because even if in the cases we have seen this implies this and this implies back the phase lock-in, frequency entrainment, you can think, for instance, in terms of two oscillators that are identical. Two oscillators are identical, they will have exactly the same frequency, but if they are subject to noise, for instance, then even if the frequencies are the same, there will be some phase diffusion between the two in the phases. So this relation for the phase lock-in will not hold. Okay, but for what we want, basically these two relations are more or less equivalent. But just to be rigorous, I write only in the right side, from left to right, this implication. Okay, so I was using the phase variable. So this means that, okay, if I go back 2 slides, here you have this, this say angular variable, theta. I can define the phase of the oscillation. I can define the movement on the limit cycle with an equation of this type, saying me, okay, the frequency or the angular velocity changes according to some function. So this is good, but in general, it's better for the next slides. And what I'm going to do is better to reparameterize your theta variable to another more convenient theta variable where the phase oscillator moves with uniform speed. So this is a simple transformation. You can see that this is not difficult. I have simply to define the phase such that okay, well, you can. Okay, if you have a limit cycle, I want to define maybe. I go very fast here and very slow here, so I want to define the phase such that here, for instance, I have, if I want to define, say, some steps to pi over n, it takes the same time going from here to here than to go from here to here. So I should have some kind of movement that is fast here, slow here, but if I reparameterize the phase variable, I can get easily a uniform phase oscillator. Okay, and this is the mathematical relation. Okay, so now I can extend this concept away from the limit cycle. In principle, okay, I'm going to interact with another, say, oscillator, another forcing, and this will change my phase. So this will make a small perturbation on the phases, on the amplitudes, and on the phases as well. So I need to extend the concept of phase away from the limit cycle. And this is done by means of the isochrones. So what are the isochrons? Okay, the isochrons define points that have, in the case of the cycle, the same future. So here in this animated plot, you can see here that you have 2 points that start at a different point, but after some time they converge on top of the limit cycle. One is on the limit cycle, and there is away from the limit cycle. So if they satisfy that they converge, after some time, you define that this is an isochron. Okay. And of course, there's an infinity of isochrons. Here, only a few of them are depicted, because there is one isochron for each phase. So I can select only, say, the multiples of 2 pi over n, some of them only. And here is, for instance, for the Van der Pol oscillator, you can see that there are some isochrons, and for any oscillator, you can create these isochrons. Now, in the next, I'm going to write the isochron next. It will become clear why the isochrons are important. For instance, on the Stuart-Landau oscillator, I can easily find the isochrons in an analytic formula. Here is the Stuart-Landau oscillator is probably the simplest oscillator. It's written here in polar coordinates with the rho and theta. You said it has a limit cycle at rho equal to 1. So the attractor here is simply a unit circle, a unit circumference. And here I have my frequency omega. When rho is 1, you see this term disappears. So so you have a uniform rotation of frequency omega. So now, if I want the points that have the same phase at all times, you see that, for instance, if Q is 0, these isochrons are simply straight lines, starting from the center. So if I'm at this point, after one period of time, I mean, if this limit cycle has a certain period, if I start this point, after one period, I come back to the isochron. Okay? But this is a quite, say, singular situation, and this is completely what we say is isochronous. But in general, if Q is not 0, then you have the isochrons are logarithmic spirals, so these straight lines become twisted. So, for instance, here, in this case, the right-hand side, if you are at this point, after one period of time, you come back here to the isochron. Your rotation is, in this case, is smaller than 2 pi. But the important point is that in one period, you come back to the isochron. Okay? And you see now why this Q is called shear or non-isochronicity. Shear is simply borrowed from fluid dynamics, shear flow. Or non-isochronicity is the fact that when this is no 0, then your flow is quite non-isochronous, because this angular velocity depends on the amplitude. Otherwise, you would rotate like a solid way. Okay, so this is an example of isochrons that can be obtained in any oscillator. But now we will see why the isochrons are important. Let's assume that you have a limit cycle written this way, and it has a small perturbation, epsilon multiplied by p, where we assume it has a certain period. Doesn't matter now. So if epsilon is small, it can be proven that the phase. Here I took time such that the frequency is equal to 1, because you can parameterize time if I want. So here is the interaction. Okay? This is the natural movement, and here is on the right side is the interaction. So in the interaction, I'm writing the gradient of theta, I mean of the isochron, multiplied by p. It's a scalar product. And here, this part, you can see a sketch of what is actually this doing. I mean, you have the limit cycle here. This is the isochron. And now you see that if your perturbation is orthogonal to the isochron, then your influence on the phase maximizes. Instead, if, for instance, I'm at this point, so at the linear order, if I make a perturbation in the direction of the isochron, it will have no effect on the phase, because if I shift my point from here to here, after some time I will fall back to the limit cycle, and I will not gain or or lose any phase. So that's why here appears this scalar product, and so the effect is maximized exactly when the gradient of theta is orthogonal to the isochron. And sorry, when this p is parallel to gradient, then you have the maximal influence on the phase. Okay, so this is the general theory of how the phase changes. And in general, if you have a certain p, so you are acting on one of your coordinates. For instance, if you have a neuron, where you will act on the action potential as an electric. So the electric potential of the neuron, the membrane potential, but you will not act on some other variables. So, for instance, for that case, you have to make the particular calculation. At the end, you will end up with a function of this form, where I already made the scalar product here. So all the effect is condensed in this phase response curve, or phase resetting curve, that is this Q of theta. This Q of theta is telling you which is the effect on your phase when you have an input here with this P, okay, for a certain P of a certain time. And at linear order, on the lowest order, is proportional to epsilon. Okay, so this Q is precisely what can be measured in experiments. Okay, in general, it's usual to distinguish between type 1 PRCs and type 2 PRCs, where type 1 PRCs have the same sign everywhere, and type 2 PRCs change the sign. So just to indicate how this works, or if you're going to write, so imagine you have you measure, say, the potential versus time, and you have a certain oscillator. It has a definite period. Then if I make a perturbation here, for instance, it will change this is what I expected without interaction, but the interaction is going to change the phase of the oscillator. So for instance, in this case, if the oscillator has a certain phase, I gain some phase difference. But maybe if I make the perturbation in a different position, it can be that I can go back in my phase. So this is indicated by this function Q, because it tells you, okay, depending on which moment you give the perturbation, you will gain or lose some phase difference, what we're expecting. Okay. So this is the simplest, say, way of seeing this. And now, okay, this is simply synchronization. So now we want to study collective synchronization. So instead of this, it was Winfrey with some heuristic arguments. He didn't propose, say, all this theory, but he proposed exactly a model that is the extension of what I said before, but for an ensemble of oscillators. So in his model, you have a huge population of oscillators. Instead, you have n oscillators, where n is large, and all the oscillators are coupled to each other. So this is a mean field theory, and all the diversity of the population is inserted here in this natural frequency omega. And these omegas are drawn from some probability density function G. So this is what introduces the heterogeneity in the population. Because this is exactly what you expect in general, that there is some heterogeneity in your population. And for the sake of simplification, you say, okay, the phase response curve here is the same for every oscillator. So all the oscillators share the same PRC, phase response curve. And this is the global signal, that is the sum of from all coming from all oscillators. This signal is introduced in all of them, and okay, in this case, this model. And this model was studied by Winfrey in 1967, and he observed that the synchronization indeed arises when the coupling is large enough, or when the distribution is sharp enough. When all the oscillators have frequencies that are close to each other. Okay. This is, for instance, an example of some present simulations we did with a co-worker at Mes Montbriot. Okay, so we took this Winfrey model here, and now take the natural frequencies distributed according to a Lorentzian distribution, for instance. Here is the PRC, a sinusoidal function. This p of theta is some pulse. Okay, for example, for n equal 10, you have here the function from minus pi to pi. So when this oscillator goes across 0, it sends this signal to the other oscillator. Right? Well, so we could obtain this phase diagram, or this theta is the width of the distribution. I mean, how much the frequencies are dissimilar, and this epsilon is the coupling. So if the coupling is small, all the population is completely incoherent. I mean, they do not feel each other. But when you cross this line, you obtain a synchronous state where there's a cluster of oscillators that is synchronized. I mean, the phases are bounded. And if you look at this capital omega here, okay, we put the frequencies ordered from the smaller to the larger. Okay, here, there's a small plateau here at 0. Do not pay much attention to this, it's because some oscillators have frequencies close to 0. But what is important is when you cross this line, emerges this plateau here, that is a frequency at which a macroscopic cluster of oscillators synchronize. Okay? And there is another small plateau here that is simply oscillator that synchronizes at twice the frequency of the basic one. Simply this is some simulations, although we could make some theory, but this is not what I want to explain here now. Instead of this, I'm going to jump to a model that is even simpler than the Winfrey model. But for this, I have to explain how to do this. So this is by the method of averaging. So if you have two systems that are oscillating and are coupled by this epsilon, this function, what we have seen is this. You can define the phases. So you go to this phase description in terms of the phases. So you have this scalar variables theta, you have this natural frequency, and now here are the couplings, where you use the gradient of the phases. Okay? At some point, I arrive to something like this. So the interaction only depends on the phases. But now the important point is, let's assume that the frequencies are close to a rational number, say 1, for instance. You can prove that the system is well described in terms of this simpler system where the interaction only depends on two functions, Q1 and Q2, that are functions of the phase differences. This now may not look so very advanced, but it is. This is much simpler to analyze than this more abstract model. Here you have only the phase differences. And of course, if you want to create collective synchronization, you will propose a model that is much simpler. But let me just, that is a school just to give you a hint of why you can go from a model of this type, that even if you made the phase reduction, still is complicated, to an equation of this type in the bottom. So you go from something that is complicated to something that is much simpler. And this is by means of averaging. Okay? So let's assume that the frequencies are close to each other. So this is small delta omega here. And this is the phase, theta 1. Okay? And this will be approximately omega 1 multiplied by t, but some slow motion phi. So I have written this in this more expanded way here. But now, if I introduce this slow phi variable, I get this. This equation is very large. But the point is that you can easily see that some of these terms are completely negligible. Because terms of this type with this omega or 2 omega, these are in this phase, in this framework, you're already rotating at a frequency that is omega t. In this framework, these terms are oscillating very fast. So they in a sense, they average zero. So only slow terms like this one will survive, while other terms, many of them, will simply become irrelevant. And this is, okay, this can be formulated in this way here, taking the integral from 0 to a large time, so you have to make this kind of integral. Okay, at the end you will see that only a term like this one, what is the phase differences, if I come back to the original variables, will remain. So this consideration allows to go from the Winfrey model to the Kuramoto model. Okay, the Kuramoto model is, again, has the same assumption, simplified assumption that the Winfrey model. It has the assumption that all the diversity is included here in the natural frequencies. The other part is common for all oscillators. Okay, its phase of the local oscillator is still here, but all the other part is the same. And and this is the sinusoidal function. It's assumed also because it makes it makes a theoretical calculation easier. In general, here it should be a certain function of the phase differences, and this function should be determined in this case. But this case is particularly tractable in mathematical terms. Okay. So if you take your natural frequencies from a PDF, simple PDF, at random, you have a distribution. So if the coupling is small, the observer frequencies, okay, plotting again, I is the index, and going from the smallest frequency to the larger frequency. I have ordered the oscillators from the slowest to the fastest. I see that, okay, there is no frequency entrainment, and if I make a snapshot of the oscillators, every oscillator has a different phase, and they are not synchronized at all. But when I cross a certain threshold, critical K, I observe what I have shown in the bottom panels. I mean, if I make a snapshot, I observe that some central oscillators are locked because the phase differences are locked, so they are synchronized. While others in the tails of the distribution, they have frequencies that are so different from the others that remain rotating at different frequencies. And you can see, if you look at the natural of the observed frequencies, you see that there is a plateau here, while the tails have different frequencies. Okay, here is at 0 because in this model you can put this omega 0 at 0 if you wish, and you can put the central frequency at 0 if you wish. But I could put a different frequency. It's not important. Okay, and I said that this is analytically solvable. I will not devote time to solving this, but I will say the main results or the main consideration. If you read any paper about the Kuramoto model, you will observe that it's important this order parameter. This order parameter is written here. It's a complex quantity, R to the I5 website. And if you imagine all your oscillators rotating on this unit circle here, this order parameter is indicating the body center, or if you wish, the center of mass of all the oscillators. And it's a complex quantity with R and psi defining it. And if you rewrite your equation here, you rewrite it in terms of this mean field or order parameter, you see that every oscillator is coupled to the mean field. In particular, if R is 0, with the mean field is 0, then every oscillator rotates free. And this is always a solution. I mean, you can imagine that if the oscillators have different frequencies, every oscillator can be rotating at its own frequency, then this state is so incoherent that the order parameter of the mean field would be at 0, and this will enter here in 0 here, so it will become perfectly consistent with the completely incoherent state where every oscillator rotates at its own frequency. But what you observe actually is that there is a critical coupling above which this solution, R equal to 0, incoherence, becomes unstable. So if the coupling is small, you observe incoherence, but if you go beyond a certain critical coupling, then you observe a synchronized state. I think when I mean a synchronized state, I'm in a state of like this one, where you observe a cluster of oscillators that is rotating with the same frequency. Okay, and this gives a certain non-zero R. And the good thing is that in this model you can compute even the critical coupling. It's given by this constant 1 pi, and this G of omega 0 is the peak value of the frequency distribution. Okay, you have the frequency distribution here, so the peak value is G at omega 0. That's the center. So you see that the distribution is very sharp. Then this G will be large, and the critical coupling will be small. And if the distribution is very flat, then this G will be small, and the critical coupling will be large. Okay? And this is, when I say writing here phase transition, I'm writing it in purpose. I could have said bifurcation. I'm saying phase transition because it's very much analogous to phase transitions in statistical mechanics, in the sense that it has some critical properties around the critical coupling, like finite size effects that are usual in phase transition in statistical mechanics. So that's why we can we are legitimate to speak of phase transition. Kuramoto, if you look at the original paper of Kuramoto in 1975, actually he derived the Kuramoto model not from the Winfrey model, or this is what he writes there, even if he was aware of the Winfrey model. He derived it from the Stewart-Landau oscillator, actually from an ensemble of coupled Stewart-Landau oscillators. So the Stewart-Landau oscillator appeared before, it's written here. The reason why the Stewart-Landau oscillator is so famous is because it comes from the normal form of a Hopf bifurcation, for those of you who are acquainted with it. A Hopf bifurcation is a bifurcation in a dynamical system that indicates a transition from a fixed point to a limit cycle. Okay? So when this parameter mu crosses 0, you go from a fixed point at 0 to a limit cycle around. So now if you reparameterize some quantities here, you arrive to this Stewart-Landau oscillator. Okay? So this is, say, the minimal model of a limit cycle. That's why it's so important. It has the natural frequency and the shear. It has the property that we showed before. So now, if I write the Stewart-Landau oscillator here in complex variables, okay, here I get this thing here. Okay? This is simply going to complex variable. And now, if I couple all of them in this diffusive way, you saw the Antonio this morning talk of diffusion. Okay, you can generalize this to any dimension, to globally coupled oscillators. You get this equation that we can call it mean field complex Ginzburg-Landau equation with disorder. There's a Ginzburg-Landau equation. It's mean field because you couple all the oscillators with all of them instead of having a certain extended system, 1, 2, 3, or 4 dimensions. And it has disorder here in the natural frequencies, omega. Okay? So now if you make a phase reduction, you can, you assume the coupling here is small, and the omegas are not far from each other. So you have this kind of system. Then you go from this model that has amplitude and phases to something that has only phases. Okay, this phase model. This is what we call a phase reduction for a small coupling. And now, if you assume that the systems are completely isochronous, this Q will be 0, and then you obtain exactly the Kuramoto model. So you can obtain the Kuramoto model from this mean field complex Kuramoto equation. Okay, as I'm saying here, absence. If Q is absent, you get the Kuramoto. But now you can say, okay, if Q is not 0, so you have some kind of non-isochronicity, you get this equation, as I said. Then if you simply redefine the omegas, you get this auxiliary angle beta from Q's, you redefine the coupling, you get this model that is called the Kuramoto-Sakaguchi model, where you have this phase lag parameter beta here. And in general, okay, you still observe a phase transition in much the same way that we observe with the Kuramoto model. Okay? So in that sense, this model is more general because you are introducing non-isochronicity, which is usually present in this way. And there are many ways to arrive to this Kuramoto-Sakaguchi model. We have seen that you can, okay, I have not proved, but you might believe in that. Using averaging, you can come to this equation from the mean field complexes for lambda equation with disorder. With the Winfrey model, you can also come here to arrive to this equation. Also from the rise of just conjunction, that studied by Pera years ago, you can, okay, using averaging, you can come to this equation. Okay? So that's, I think that's the reason why this equation is so important. It appears in several contexts. Okay? And the Kuramoto model has been used in a lot of studies. Here I just listed three. The rise of superconducting just conjunctions. Studied by Pera, whether they this is kind of array that is using this superconducting quantum interference device or something like this. That is an array in a loop to measure small variation of the magnetic flux, I think. Also, some variation of it in semiconductor lasers. Even you can find a paper of collective neutrino oscillator. I took a look into the paper, and they simply propose a model where if the neutrinos change the flavor and they are in a supernova, they are so concentrated that even if they interact weakly, they can synchronize in a certain sense. Believe it or not. But there are a lot of extensions of this model, and that's why it's famous, depending on which you want to study. You can include the stochastic or periodic forcing. So you can imagine that you have your oscillators and still you have a second forcing from day and night. So you can put time delay, for instance, from the crickets. Maybe what you see when a cricket here, the other cricket, there is some delay in the time. The cricket, the sound, it's arrived to one cricket. Of course, there is a lot of works in the Kuramoto model in a lattice or in a network. In a lattice, the critical dimension is 2 for those who are acquainted with this concept of statistical mechanics. You will consider the oscillators are moving. You can consider more distributed parameters, not only natural frequency, for instance, the shear. You can also include second order derivatives in time, in which case, in some limit, you arrive to the Hamiltonian XY model. So okay, there is a lot of variations and extensions on this model. And in fact, okay, there is a review on the model in 2005, though many developments have been done since then, so maybe in not so long time they should write another review, probably. Okay, and I don't know how, okay, time. So I have a couple of slides, so something I did like a couple of years ago with Ernest about this model that is the Kuramoto model with distributed shear, where we assume, if you take the mean field complexes Orlando equation, you assume that the distribution is not only in the natural frequencies, but also on the shear, we'll come to this equation. So this is the same equation that we had before, but now you have this QJ here. So now there's disorder not only on the frequency, but also disorder on the shears relative to this equation. You can also arrive to this equation from the Winfrey model with disorder on omegas and disorder on the PRCs. So I think this equation is particularly important among, the extensions in the Kuramoto model when you put disorder on several parameters. So, okay, we found, for instance, distributed natural frequencies and shears in a recent way that incoherence was always stable, no matter how much coupling you introduce, because the coupling depending. Okay, here if you don't have disorder on shear, this gamma is 0. So this you get this formula. This is Kuramoto's formula. So it can be extended in this way when you have disorder on the shear. So it's. But I will overview here simply some take-home messages for you. So simply, what they have said is, okay, we have synchronization. If we have with coupling, we should go to a phase model or a phase description. So because you have a limit cycle, so perturbations on the amplitude are negligible. What's important is the phase. The phase is, so to speak, is neutrally stable. And perturbations on the phase are important. So if you're in weak coupling limit, you will always be able or should be able to to make a phase model and a phase setting group. From here, if you go to macroscopic synchronization, the most natural extension would be something like the Winfrey, would be exactly the Winfrey model. Where you put exactly your PRC and you put natural frequencies here distributed in certain way. Now, if you make an additional assumption that the frequency diversity is slow, so I mean, more or less, or they have similar frequencies, you perform averaging, and this in particular implies that you go from the Winfrey model that you have here to some Kuramoto model where you have some function that is function of the difference of the phases, and in particular for the Kuramoto model is the sign of the sinusoidal function. This is the overview. These are some books I can recommend. Also, I took some material from the Scholarpedia, the book of Kuramoto, that was in 1984, but was reprinted in 2003, or it was on a course in CKB's book. All these books more or less contain what I explained here, and that's all, and I thank you for your attention.
So, are there any questions for the talk?
Something you mentioned at the end. In order to derive the Kuramoto model, you need a small deviation in the frequencies. And usually the Kuramoto model is used with a Lorentzian distribution frequency.
Yeah.
It has an infinite value.
Yeah.
Some sort of inconsistency right in
Yeah.
there.
No, it's yeah. You should. Okay. Yeah. You should take some care because.
No, why do you have the model? The model is there.
You make this and then you ask. Yeah. And basically, okay. I can tell you that this is how to say. You are right. I mean, you have something that has this. You have to be. You are not sure how much is the weight of the tails, the distribution. You have some distribution there that have very large distribution, so you may have reasonable doubts if this is working or not. So what you can do is to compute the phase reduction, and now I can compare the simulation. And actually, if the simulation is if the width of the Lorentzian distribution is weak, is small, it works. I mean, actually, for this panel, I can do it. That the solid line is the theoretical line, and these circles here are the circles computed with the Stewart-Landau oscillators. So oscillators that have amplitude and phase. So you are right in a sense, but it can work.
Other questions? So if not, we thank the speaker again.